This video is going to show you how to find the electric potential for point charges and how to use it to solve word problems. To begin with, we need some way of comparing our energies, and so we do that by this process of normalizing. We normalize values to compare them. For example, let's say you go job hunting. So you're out and you're going job hunting and you find these two jobs. One job is $20,000 a year, the other job is $25,000 a year. But when you think about it, they're not quite the same. So you look a little bit closer at the jobs to figure out which one to choose, and you realize that one job is going to pay you $13.88 per hour and the other job is $13.02 per hour. So when they were advertised, they were normalized one way, and now when you actually look at the details, you see they're normalized a little differently. It's the cost per charge. So by normalizing it, it gives you a way to compare these two. And you look at it a little bit closer and you realize the job that was advertised for less actually pays you more per hour. So this is done because you work less hours. So you have a choice there. Look at the hours that you're working and try to decide which job you're going to take. So you had to normalize it in order to figure out which job is which one you wanted to choose. We can do the same thing for energy. Let's say we have this potential energy, or we're looking for the potential energy of this mass that's 1 kilogram above the floor. Well, mgh, 1 kilogram, 1 meter, let's say g is about 10, so that's about 10 joules. Let's say we look at that for 1/10 of a kilogram per mass, 1 meter above the floor. Well, it's 1/10 as much, or about 1 joule. So we've got a way of comparing our two energies based upon the mass. How about the stapler? If I know the mass of the stapler, then I can figure out what its potential energy is when it's 1 meter above the floor. So what I'm doing is I'm normalizing everything by looking at the energy per unit mass. By defining it as 1 meter above the floor, then I know if I know the mass, I know how much energy it has. So in order to find out how much energy, all I need to know is find the mass, and everything's easy to compare. I can compare it per kilogram that the object has. Well, let's say I did this and the scientific community liked it so much, they actually named a special unit called the waynage after it. And the waynage is our way of looking at the energy per kilogram for an object that's raised 1 meter above the floor. So that's great. Well, in reality, there isn't a unit out there that is normalized like this energy per unit mass, at least for this kind of energy. But there is a unit out there that is normalized for electrical potential energy, and that's the energy per unit charge. So what we're looking at here is this potential difference, this potential energy, and potential difference is the difference in potential energy per unit charge. So that's called potential difference. So you'll hear that term a lot when we're talking about word problems. Finding the potential difference. So we're just finding the difference in two energy levels and dividing it by the charge. So now we've normalized our energy. The potential difference is also given its own unit. It's called a volt. Or you may find it when people ask, what's the voltage? Well, that's the potential difference, and that's the energy per unit coulomb. So a volt and potential difference, it's a form of energy. It's just normalized, energy per unit coulomb. The nice thing about this is it's a scalar, so direction isn't going to be an issue when we're solving the word problems. It's just a matter of finding numbers and adding them up. Let's take a look at an example. I've got a large charge. It's going to exert an electric field. I'll take a small charge and move it close against the electric field, and it's going to feel repelled the whole time. Now that's Coulomb's law, pushing the two charges away. So if I look at this, I can see there's an electric field around it, and what I'm doing is I'm working against the electric field. So I'm working against this force. Well, that's work, force, and distance. And that's where the energy is coming from. So let's take a look at this again in terms of the math, our little model here. So I've got this particle, it's separated by some distance, and that can be the distance I'm going to move it eventually, close to the particle. So I've got work is equal to force times distance. I know the force comes from Coulomb's law, that's K Q1 Q2 over R squared. So I can substitute in for work the equation for Coulomb's law. So FD becomes K Q1 Q2 over R squared times R, where R is just replacing the distance because that's what will happen if I move it all the way in. So the R's will divide out, leaving me with K Q1 Q2 over R. So that's my expression for the work done in putting the particle there. But I'm looking for the electric potential energy. Well, that's defined as the change in energy over the charge, which is defined as work over charge. So if I take my expression Kq1 Q2 over R squared and divide it by one of the Q's, then they're going to go away. And that's going to leave me with the electric potential equation to be Kq over R. So that's how I can find the electric potential at a point in space if I bring the charge out from infinity where we measure it to be 0. So if I move the charge out to infinity, I take the limit of that as R goes to infinity, then my value becomes 0. So that's where our 0 point is. We always need some way of looking at what's 0. With kinetic energy, it's when there's no motion. With potential energy due to gravity, it's wherever you call the height to be the lowest point of the motion. For a spring, it's wherever the equilibrium is equal to 0. And for this electric potential, it's whenever you take a charge and you put it at an infinite distance away from your point. That's where you call it 0. So let's take a look at an example. Let's find the potential difference if a charge is moved from infinity, that's where it's 0, to an indicated point in space. That's a little dotted line there. So I've got these charges all around it, and they've got some distances to them. So I'm going to use my potential energy equation, V is equal to kq over r, to figure out what's going on. Now, when we did electric fields and we did Coulomb's law, when we actually found the magnitudes, we dropped the signs of the charges. It didn't matter if it was positive or negative, because we used that to determine directions in an earlier step. But with electric potential, you need to keep the signs this time. So electric potential, it's a scalar, and you got to keep the signs. So it's a matter of plug and chug. The electric potential at point A is kq over r, and that gives me my one value. For B, I just put in my kq over r. That gives my second value. For C, kq over r, my third value. And finally, for part D, kq over r, and that's my fourth value. Notice my negative signs. This time I'm keeping the negative signs because I'm looking for a scalar answer. So to find the net electric potential, I add them all up, VA plus VB plus VC plus VD, and that gives me a value of negative 47.62 joules per coulomb. But we don't use the joules per coulomb. Instead, our standard SI unit is a volt. So negative 47.62 volts. And this is the same volt that you see when people talk about the outlets of your house, or they talk about batteries, or anytime they talk about volts, they're always talking about joules per coulomb, this normalized unit of energy. Thanks for listening.